This course, what I'm calling NMath B, Engineering Math B, is primarily about solving partial differential equations, certain more of them. We've gone through quite a bit where we use the product method or the separation of variables method for solving them, even in different coordinate systems. We're going to get into using Fourier transforms to solve partial differential equations. But we need to talk about Fourier transforms before we do that. And we're going to get to Fourier transforms by way of the Fourier integral. Right now we're talking about the Fourier integral. And spoiler alert, what is it? It's basically the analog of the Fourier series. We've covered the Fourier series earlier in the course. But remember, a Fourier series was only a way to match a function over a finite extent. Like say this were the function, you could get a Fourier series to match it from -1 to 1. And then the Fourier series would converge to a function that just as this function repeated every 2 units of time or whatever the interval is here. Or you could match it from -2 to 2, or from any finite number over a finite extent. What if you want to match this function, for example, over the whole real line? Well, again, you could derive this one of 2 ways anyway. We could start with the trigonometric Fourier series, take a limit, or we could start with the exponential Fourier series, take the limit there, and each way you'd get the corresponding Fourier integral, either the trigonometric Fourier integral or the complex corresponding term, the complex or exponential Fourier integral. So we're going to start with the trigonometric Fourier series. And if you put it all together, including the formulas for the coefficients are in parentheses. So this whole thing is the Fourier series, all put together. What we do is, here P is the extent. Like if the Fourier series were to match it from -1 to 1, P here would be 1. We're going to take the limit as P goes to infinity. But you have to be a little bit clever about that. I'm not going to go through that. If you want the outline of that derivation, email me and I'll send you my typed up notes. That goes for anything in my course. But if you do that, if you take this, which is really a Fourier series, and take the limit as the P goes all the way out to infinity, you will get these formulas. These sums here become integrals. And what used to be only take on non-zero values of discrete arguments, these coefficients now are over the whole real line. So this is the Fourier integral, and these are the formulas for these coefficients that are inside that Fourier integral. So let's talk a little bit about the Fourier integral. Well, for one thing, if your function is even or odd, it simplifies. So we have simplified versions for even functions and odd functions. And just like the Fourier series, any place in the function, the original function is discontinuous, Fourier integral converges to the midpoint of the left and right. That'll become important in a little application here that we're going to get to in a bit. So let's take this example. Say you were given this. Well, it helps to plot what that looks like. Now look at this. It goes out all the way to plus infinity and minus infinity. Unlike the Fourier series, it goes on forever. We're going to match this over the entire real line. And note, it's easy to tell when you graph it that it's an even function. So we're going to be using this column. First, we'll calculate what this A of alpha is, and then put it into this formula. So here's what A of alpha is. Notice that when we do this, we only need to worry about positive x. So we only need to worry about over here to the right. It's all 0 except for this interval from 1 to 2. So we only need to integrate from 1 to 2. And there the function is just constant pi. This is from the formula. So that's an easy integral to take, and you end up with this with E of alpha. Then you put it into the other formula. Well, here you go. Here is our Fourier integral. It will converge to this function, which looks exactly like the original function. And at points of discontinuity, it converges to the midpoint of the left and right limits. So here is actually the Fourier integral. One use of it is to evaluate impossible integrals, or actually integrals, definite integrals that don't have a corresponding indefinite integral. So let's say you wanted to take this integral. This looks an awful lot like the example we just did, which said this, where what this f is this thing. It's graphed here. Here's the f of x that corresponds to that. Well, if you compare this to that, just substitute in pi over 2 for x. We'll have what this integral is here on the right. 2 times it. Plug in pi over 2 for the argument of the function. And at pi over 2, let's look at that. Pi over 2 is somewhere in here. Whatever half of pi is, it's somewhere around 1.5. 0.6. Here the value of the f is pi. So we have pi equals 2 times this integral. So now we have a formula for this integral. Pi over 2. So we could find a way to evaluate this integral, even though we couldn't take the indefinite integral. Here's another example. Say here it is, and if you graph that function, it looks like this. We'll first find the Fourier integral, and then we'll have the second part of the problem. Use that result to evaluate this definite integral. So in this case, if you look at the graph, it's a odd function. So we use the formula for the odd function. We'll have to take we're going to have to evaluate an integral that I'm going to use a table lookup for that. Like, not sure how you do it, maybe integration by parts or something. We'll use a table. So the b of alpha, here's the integral we have to take. We only have to take the integral over positive values, and there it's just x from 0 to pi. So we only integrate from 0 to pi, x times, this part comes from the formula for the Fourier integral, which becomes this. I'll multiply by alpha here and another alpha here, so it looks like this thing in the table. Make up for it, I have to divide by alpha squared. So now I can use the table. Evaluate that from x equals 0 to x equals pi, and I get this. put it in the formula from that table we had. And you have this for the Fourier integral. Now this integral looks a lot like that. Let's see. Up here we have pi alpha, and here we have alpha x. So we want to make our x equal pi. Here's the catch. That's right at this discontinuity. So our f of x at pi is actually this midpoint here. This vertical extent is up to pi here. So right at the argument of pi, the f of x is actually, f of pi is actually pi over 2. That's why you got to be careful of those points of discontinuity. So we're trying to evaluate this integral, and it looks like this integral where x is pi. So what is f of x at pi? Is pi over 2. So we have all this equals pi over 2, or the integral we're looking for is pi over 2 times another pi over 2, or pi squared. So anyway, that's the basic trigonometric Fourier integral. Next time we'll get into a complex form of it. Will then lead us to Fourier Transform, which is what we really want to do for partial differential equations.